Let us do checkpoint 6.36. They want us to calculate the flux of F, which is x cubed, comma y cubed, across a unit circle oriented clockwise. All right, let's get our circle going. Our unit circle oriented clockwise. And let's write our Green's theorem. But this is actually a special case of Green's theorem. We call it Green's theorem in flux form. And there's going to be another name for this later on. Later on, it's going to be called the divergence theorem, but we'll see how that ties in with the name. All right, so according to Green's theorem in flux form, we have a line integral over a closed curve C of P, well, it's not P dx, it's actually the vector field dotted with a normal vector ds. So instead of seeing how it compares to the path of the curve, which is sometimes called circulation, it's comparing the vector field with the normal vectors of the curve. So this n is normal vector. Now we can compute this straight ahead using line integrals. Well, we learned that in the, I believe it was in section 6.2. But instead of doing that, we will use Green's theorem, which in Green's theorem tells us that this is actually equivalent to the inside of that curve C, the region inside, which is D. So let's say D was the inside of that circle. And this is going to be the partial of P with respect to X plus the partial of Q with respect to Y. So it looks very close to Green's theorem. Green's theorem has a negative, and then the P's and Q's are switched. But again, this is flux form, the flux form of Green's theorem. So we'll just go ahead and use that directly. And instead of doing this double integral, or instead of doing this line integral, we will do a double integral instead. So we need a few things. We need to parameterize, or we need to figure out how this region looks like in D. And since this is a circle, I probably would be interested in knowing the polar coordinates with this. And in polar coordinates, this is a unit circle, so the r is just going to go from 0 to 1, and our theta goes all the way around from 0 to 2 pi. Next thing we're interested in is finding out what these values are. So the partial of p with respect to x. P is the first component of your vector field. That's going to be 3x squared. The partial of p with respect to y, or q, sorry. Partial of q with respect to y is going to be the derivative of y cubed, which is 3y squared. Now, if we put that into the double integral, according to Green's flux theorem, we're going to put that into the double integral of d, and then we have 3x squared for p dx, and q dy is going to be 3y squared dA. I can factor a 3 out and realize that this is an x squared plus y squared, and so even more motivation to go into polar coordinates here. So let's go into polar coordinates. At this point, we're going to say that this is r squared, but our dA transforms to an extra r. dr, the r limits go from 0 to 1. The theta limits go from 0 to 2 pi. All right. So we have a 3 on the outside. Theta is independent of the integral inside, and so I can just do that integral separately and do a multiplication. And our integral is just going to be r cubed. And so we have a 3. This whole thing is just going to be 2 pi. when we integrate that. This is going to be r to the 4th over 4, but you're going to integrate from 0 to 1, so it's just going to be 1/4. So we have 3 times 2 pi times 1/4, and that would give us a 2 in the denominator. So this is 3 pi over 2. All right. Good luck.